So, now we are going to start with the transition state search. So, transition state search is going to be one of the most exciting topic in this course. This week we are going to keep the theory part to the limited, because in many sense transition state search is not a science, but it is an art. So, you have almost be like an artist to get the proper transition state, and it requires a lot of practice. So, we will show you some techniques how to do it, but only practice can make you perfect. So, transition state, as you know, is essentially the first order saddle point through which the two local minimas are connected. So, it is like the reactant will start from here through this saddle point, it will go to the product. And this generally the one of the easiest way to find out the transition state is to get to a geometry close to the transition state. Otherwise, so you need to have some kind of a guess, and the guess can come from your intuition. You may already know the answer, or maybe God has already told you what is the answer, but somehow you need to have very good guess. One way is to find out an internal coordinate that actually resembles the real reaction coordinate, and then you run a relaxed surface scan, find out the maxima along this internal coordinate, and if you do few times trial and error, you will find out the transition state there. So, let us think of a very simple SN2 reaction CH3F, and the Cl minus actually substitute the fluorine by chlorine, and you get chloromethane from fluoromethane. And in this case, that why I am taking this very simple reaction is that the reaction coordinate is very straightforward. So, this is my fluoromethane is. So, the chlorine will come around, it is a standard SN2 reaction. So, the chlorine will come in and the fluorine will go out, and this is how the transition state looks like, hopefully. So, at least we know the internal coordinate. So, along this coordinate, actually this is my reactant, and along this coordinate it will cross the barrier. Now, to do the relaxed surface scan, the keyword is that in this case we are going to use a semi empirical method PM3, and if you do the geometry scan, so this is the keyword for scanning. So, this is the bond between 5th atom and the 0th atom, and it will scan from 3.0 to 1.2 using 15th step. And do not forget there are two end to the block, one is to end the scan keyword and one is to end the geometry keyword. Now, question is that why I have chosen this keyword 3.0 to 1.2. So, to understand that, first we need to get the reactant and the product. Cl minus geometry we know, and as well as the fluorine minus also, because it is just an atom. So, let us first get the geometry of methane and fluoromethane. So, up to now we were mostly using Avogadro. For chloromethane and fluoromethane we still can use Avogadro, I believe. So, let us go to Avogadro. So, it is carbon, and one of the hydrogen I can just replace with fluorine. I do not need to adjust the hydrogen. I make the Orca input file. This is a simple molecule, and we have given a good geometry. So, hopefully it will optimize without any frequency calculation or anything. It is a good idea to even to give the frequency keyword. So, we make a folder called TS. So, it is CH3F. I am already in that folder. If you are not there, what you can do is you can go to the folder, and you see that now I am using only MobaXterm, because it is really convenient to see how the output file is running and how much time it will take. It is easier to guess. Let me go to view terminal, zoom a little bit more, so it becomes more easier to see what I am doing. So, it is Orca So let me run the calculation. What I can do is that instead of fluorine, I can take a chlorine, I can replace it. I make a PM3 opt and frequency. CH3Cl. So my calculation is still running. CH3F. So my optimization is done. It's calculating the numerical frequency. By the time it does its numerical frequency, what we can do is I can also run the CH3Cl job. Although few times I advise you against to run parallel jobs. So what happens if I run more than one job together? It start to share resource. You know the modern CPUs has more than one core. Like if you have an i7, it will have a 8 cores total. And also, but it also, and the RAM is generally sufficient. RAM is not the problem in most of the cases, but somehow it will start to share the cache memory as well as the IO will be shared. So this tries to slow down most of the job. So in most of the cases, it's not too a good idea to run more than one job together, but sometimes we get impatient, and also it will heat up your laptop. But sometimes we get impatient and we run more than one job. In high performance clusters, generally there is a dedicated cooling facility which will cool down the cluster, so the heating will not so much of a problem. F dot out. So my frequency calculation is done, and all the frequencies are real. So this is a minima. Generally, in this kind of simple calculation, it's unlikely that you will face a problem. My CH3Cl job is still running. I hope that they are in the frequency calculation also. Optimization is done. Yeah, it's also doing its frequency calculation, so it will be done soon. The frequency calculation is done. So all good. Here also all frequencies are real, so it's a real local minima. Now let us open it with ChemCraft. Let us start with the fluorine. So except this initial optimization, we are mostly going to use ChemCraft here because this is ChemCraft is generally now the most easiest thing to do for finding transition state. The various steps which is involved, this is more easier to do with ChemCraft. So it's 1.07. Okay, and for the chlorine, is 1.78. So you can think that chlorine bond length will be higher. Now to make the relaxed scan, what I should do, I now should put a fluorine here. I go to the edit option, add atoms, maybe I should bring in a suitable orientation. I want to put a fluorine atom here. Now, to make sure that they are aligned, what I should do now is to make sure the angle is 180 degrees. So, it is now currently 166. Let us make it 180 degree. And now, if I try to look it, we can see that they are aligned. Maybe quickly it will be a good idea to check the distance is 1.27, should be fine. And I save it as save structure, simple XYZ format, atoms as character, CH3Cl.F. I think the name is fine. Now, let us prepare our input file. So, this is my input file. Do not forget that there are two ends to the geometry block. Let me open this file using again notepad. Good, we got it. Let me get the geometry. And this one should be star XYZ, they should be -1 because chlorine or the fluorine will be minus here, multiplicity is 1. Now, you see the ORCA start the calculation from 0. So, carbon is the atom number 0 and 5 is the atom number of fluorine. So, I am scanning, I am changing the bond of chlorine to fluorine at 1.2. And if I again go back and I hope I have the fluorine geometry, and this bond length was 1.35, the fluorine and carbon. So, to get the this is optimized geometry and this is the bond length 1.35. So, that means this is my equilibrium geometry. So, if I have to see the transition state, what will happen in the transition state, the fluorine bond will elongate because it will now go out and the chlorine will come from this side. So, the chlorine bomb will start forming. So, at the transition state, this fluorine geometry will be somewhere between 1.35 and infinity. So, maybe around 2 or 3 something somewhere. So, around 3 4 we can consider as infinity in this case because the interaction will be very less. So, that is why I am scanning from 3. Now, you may ask this question, why I am scanning up to 2, it is 1.35 is the equilibrium distance, it is unlikely that it will go beyond the equilibrium for transition state, it cannot go in this way. But generally sometimes there is interesting features of the potential energy surface around the equilibrium. So, it is a good idea to scan a little bit more. So, what I will be doing now is that I will changing this bond and optimizing all the other bond including the chlorine bond here. So, I will know as I change my fluorine bond how the other bonds will look like, and by doing that I can get the maxima which will actually correspond to the transition state or very close to the transition state. It may happen that I do not get it in one chart, so maybe I have to do another iteration. So, this is now there. So, let me save as, scan rel dot inp. So, I am in the same folder. I have not saved it in the same folder or what. Let us see it. Sometimes this kind of mistakes happens. No, I was saving in a wrong folder. So, this is where I should save, in the folder ts scan underscore rel all files, and this has to be input. So, this is now here. So, let me run it. So, let me close these ChemCrafts so that my job runs little faster. So, sometimes the initial optimization can take some time. Generally, scanning at the large distance, generally doing this relax optimization actually takes more time than when it comes to closer, because there the bonds are very well defined. When it is far away from the molecule, like at 3.2, then it may take some time to do the first optimization step. So, we are almost there. So, it is there total 15 step, I think it is 11th or 12th step is running on. I think it is 12 running, so 3 more. So, this is step 14. So, this is almost at the equilibrium. One more step after this. This is, I believe, is the last step of the scan. So, it has taken total 20 minutes to do this calculation. So, this scanning is an expensive business. So, now let us open the scan output file, and actually ChemCraft can give a very nice visualization if you open the output file. Now, you can go to view scan graph and energy versus scan step. This is how it will look like. So, you may think that this is actually where the maxima is around. So, this may be close to transition state. Let us see it. So, let us go to the scan dot trajectory, where all your trajectory files are there, and this also I open with ChemCraft. So, all the geometries are there. So, it will be a good idea to see it. Only thing I want to see it quite fast. So, I will animate the optimization step and see what happens. So, this kind of bond breaking will be observed. So, initially the fluorine atom was abstracting hydrogen to make it an HF, then eventually around this point this is actually forming the HF. So, from this one the idea of scanning may not be very good. So, let us do then. So, now we have to be careful. So, this is step 1, this is point 1. So, then this will be point 10, that means this is point 11. So, this point is actually point 11. So, because if you start here this will show as 1. So, now let us go and open the point 11. This is, you can open with Avogadro also, but I would open with Chemcraft. So, this is also not where the reactant is in a proper form. So, that means this is may not be the real transition state. So, maybe we have to go into the higher variants. You can open with Avogadro. I think this will be close quicker than opening in Chemcraft, not really. So, this is where it at least gives you some kind of 13 at least it is in a proper orientation. So, either we have to start with 12 or 13 and then redo the scanning again. So, let me open the 13 with Chemcraft. No, Chemcraft I have to open it with the notepad, copy the geometry, and redo the scan with the new geometry. And hope that this time scanning come proper. So, it always a good idea if you do the scanning, you reopen your trajectory and try to see how the scanning is going, because just getting a maxima in the potential energy surface may not be the real transition state. Here we are getting a transition state if you open the optimization 11, but that is not the actual transition state you are looking about. So, you could have, of course, I could have seen it from here also. Like I was getting this one as a transition state, but this is not actually the transition state what we are looking for. So, this will give me something wrong. So, you have to always use your chemical intuition. So, now I have changed my input file. So, I have to run this job again. Hopefully, this time the convergence will be slightly faster. So, we are almost there. So it's there total 15 step, it's I think it's 11th or 12th step is running on. I think it's 12 running, so 3 more. So this is step 14. So this is almost at the equilibrium. One more step after this. This is, I believe, is the last step of the scan. So it has taken total 20 minutes to do this calculation. So this scanning is an expensive business. So now let us open the scan output file, and actually Chemcraft can give a very nice visualization if you open the output file. Now you can go to view scan graph and energy versus scan step. This is how it will look like. So you might think that this is actually where the maxima is around. So this may be close to transition state. Let's see it. So let's go to the scan dot trajectory where all your trajectory files are there. And this also I open with Chemcraft. Since all the geometries are there, so it will be a good idea to see it. Only thing I want to see it quite fast, so I will animate the optimization step and see what happens. So this kind of bond breaking will be observed. So initially the fluorine atom was abstracting hydrogen to make it an HF. Then eventually around this point, this is actually forming the HF. So from this one, the idea of scanning may not be very good. So let us do then. So now we have to be careful. So this is step 1. This is point 1. So then this will be point 10. That means this is point 11. So this point is actually point 11. So because if you start here, this will show as 1. So now let us go and open the point 11. This is, you can open with Avogadro also, but I would open with Chemcraft. So this is also not where the reactant is in a proper form. So that means this is may not be the real transition state. So maybe we have to go into the higher variants. You can open with Avogadro. I think this will be closed quicker than opening in Chemcraft. Not really. So this is where it at least gives you some kind of (13) at least it's in a proper orientation. So either we have to start with 12 or 13 and then redo the scanning again. So let me open the 13 with Chemcraft. No, ChemCraft, I have to open it with the notepad, copy the geometry, and redo the scan with the new geometry. And hope that this time scanning come proper. So it always a good idea if you do the scanning, you reopen your trajectory and try to see how the scanning is going, because just getting a maxima in the potential energy surface may not be the real transition state. Here we are getting a transition state if you open the optimization 11, but that is not the actual transition state you are looking about. So you could have, of course I could have seen it from here also. Like I was getting this one as a transition state, but this is not actually the transition state what we are looking for. So this will give me something wrong. So you have to always use your chemical intuition. So now I have changed my input file, so I have to run this job again. Hopefully this time the convergence will be slightly faster. So now my calculation is done. It took 7 minutes. Now let me open the scan.out. I would have run with the same name, so it actually has overwritten the previous file. So open with ChemCraft. So if I now see the scan graph again, I see a minima, maxima here. So it's at 0.8. Also, as we have done before, we should also see the trajectory to see that are we looking at the correct trajectory or not. So this is the trajectory. I open with ChemCraft. So I want to animate it, make the step time as 0.5 and animate optimization step. So here at least you can see it gives you the correct behavior. Of course, we are seeing the reverse one. We are seeing the chlorine is leaving and fluorine is joining, but it can give us the transition state anyway. So this time at least through the scan we have identified the correct internal coordinate which corresponds to the reaction coordinate. So you need to do few times trial and error sometimes to get it, and now we need to get to the step where it is we think it's close to the transition state. So this was our graph. So this is 0.8. So we can make a new file. I have closed my PowerPoint. So what happened due to the scanning is that it has traced a minimum energy path along the reaction, and so of course the work output will give a final energy of the scan, and you can ChemCraft you are directly visualizing it. Now as we have got the correct point, so now it is close to the transition state. So now we will run a transition state search, and if you see the keyword, so instead of opt we will use an opt-ts, so that it will actually optimize it to a transition state. and after that we need to calculate a frequency calculation to make sure that it has actually optimized to our transition state. And the geometry block, we have to provide the initial Hessian because it need to follow the negative frequency, and for PM3 there is no analytic frequency available, so you are going to use numerical Hessian. If you are using some other DFT method, you could have skipped this line, and at each step we are going to recalculate the Hessian. So let us make the input file then. And we have seen that the step 8 was actually close to the geometry. So what we can do, we can use the XYZ file format. I could have copy pasted the geometry, like the geometry also, it's -1 1, and it's I just need the name, so just copy the name. This is scan.rel, and this I can save as maybe final LTS .inp, and now I can run the calculation. Where is my final LTS? It's Orca. This usual problems. So it says that scan.rel file is not available. I have not given the name XYZ. Don't forget that file name actually contains an XYZ. No. I have to retype it again. Out ampersand. Now it's running. There's some problem. Let me see the input file again. So now the calculation is running.